so far? We've learned about 13 different theorems, right? We've learned about 13 different theorems. But those theorems on their own are useless. We've got to apply them, all right? So let's go example by example. I'm not going to resolve them. I'm just going to say, so one part of this example, and probably Krish did not write it out over here, is the idea, the overall or overarching idea is that we want to reduce the hardware, okay? So you have, let's say, in example number 1, which we did on last week, Thursday, if you draw that in hardware, if you draw the circuit for it, which you should now be able to do comfortably, you will see that, let's do a quick quiz over here. How many gates do you think are there in lecture 3, week 4? How many gates? Example 1, sorry, example 1. How many gates would there be? Okay, some people say 4, but in reality, if you look at it, if you take into account there's a not here, there's a not here, there's a not here, right? So it might end up being 1, 2, 3, 4 is the OR gate, 3 AND gates, 4 OR gates, 1 OR gate, and 3 NOT gates, right? So 1 OR gate, this 3 can be ORed together. You have 3 AND gates, 1 to end this 2, 1 to end this 3, 1 to end this 3. But how do you get B bar, B bar, C bar? Right? So you can use 2 NOT gates over there, not 3, 2. Because when you make the B bar, you can recycle that B bar, right? So you've got to think. So sometimes I will ask you, how many gates are used over here? And the answer in this case is 1, 2, 3, 4, 5, 6. 6 gates. And in the end, after applying Boolean algebra, all those Boolean theorems which we have become familiar with, we end up with finding that G is equal to A. So instead of going through this big circuitry which has 6 gates, we just connect A to G. All that circuitry is eliminated. So how many gates do we end up with in the end? Final answer. We go from 6 gates reduced to how many? 0, right? So that's a total cost savings. So your total costs have been saved, all right? Okay, let's have a look at example 2. Let's do a warm-up on example 2. Guys, once again, very similar thing. How many gates? 1, 2, 3, 4. 4 OR gates, 1 AND gate, and then you have 1 for A bar, 1 for B bar. So 4 gates, 1 AND gate, 5, 6, 7. 7 gates. And in the end, our final reduction comes to what? G is equal to 0. So we just connect G to ground. You don't need any gates. Again, 100% savings. 100% savings. All right? Okay? So my point is, whenever we do something like this, the idea is that we are not doing something in algebra that we are reducing. We are actually playing with hardware, right? When you are doing Boolean reduction, you are changing the nature of the hardware, right? So over here you had this particular long rule, and it came down to just A bar or C, right? So once again, we have reduced, so down to 2 gates, I believe, 1 for the NOT and 1 for the OR, right? So we have reduced the hardware. That's the main point I want to make over here. All right. And you can see, so my point is that you should be able to do this. Let's now have a look at one more example. Oh, okay. We went all the way till example 6. Okay, we went all the way till example 6. And example 6, for those of you who recognize it, that is from where? Where is that from, guys? That's from your tutorial last week. If you look at question 5 in your tutorial last week, you will find something like this. Okay. Now, we were doing this, we were reducing that. Let's now finish it off. So, how can we write it out, guys? Now, a key point over here, guys. Let's put a pause on this particular example. I want to introduce you to another concept. I would like to introduce you to another concept. So today's date is, what is it today? Lecture 1. All right. And what date was it on the other day, on Thursday? Does anyone recall the date from last week, Thursday? All right, guys. All right. I want to introduce you to something else, which will maybe allow you to then give you the gateway to go and change it. Okay. So let's talk about the XOR gate. Let's talk about the XOR gate. Exclusive OR, right? It's an exclusive OR. A, B, X. So the symbol you guys are all familiar with. A, zero, 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 one, one, zero, one, one. Okay. All right. Now, the way to remember exclusive OR, and I think we've already covered this, so this is a revision. So one of the funny ways I remember this is, so let's say this engineering student is a boy. He's got two girlfriends, two possible girlfriends, girlfriend A and girlfriend B. All right? Okay. So if girlfriend A says no to his marriage proposal, right? So that's a 0. And girlfriend B says no, he ends up with no wife, right? If girlfriend A says no, girlfriend B says yes, 1 means yes, he has one wife, so he's happy, right? If girlfriend A says no and girlfriend B says, girlfriend A says no, yes, and girlfriend B says no, he'll still have one wife. But if both says no, he'll still have nothing, all right? Or both say yes, then he'll still have nothing, okay? All right. How many of you have been in that situation? Nobody, okay. All right, good, good, very good. All right, okay. So what I wanted to show you over here is that another way to break down our XOR, we write it as A, that's the symbol, XOR B. Now, another way to write it down is we have A and B bar, or A bar and B. That's the algebraic expression for an XOR. That's an algebraic expression for an XOR. The way we got it done is, and we'll do lots of this later, is you look for the ones. We look for the ones on our truth table. You have A is 0, so that's A bar, and B. And over here, you have A and B bar, right? And you put it all together. We'll do a whole exercise on this later on. All right. So our circuit comes to be, our circuit for A XOR, that can be broken up . There we go, guys. A more professional way to draw it is, if you remember in the tutorial, we would say B, we'll just pick up B, and we'll do this. That's a more professional way to draw B. All right. Okay, and similarly, we can do something similar for A as well. All right. I've forgotten to mention something over here. Sometimes some people write it like this. That's because it's commutative, you can write A bar and B, or A and B bar. A and B bar. You can just flip it around because it's commutative. The OR gate is commutative. Right? Now, this knowledge then allows you to attempt this particular tutorial problem. And I'm going to leave that for now. Right? I'm going to leave that for now, leave some space. I want you to use that knowledge now. You now know this has been given here, and you expand it accordingly. All right? And then eventually, this becomes very small. This becomes very small, okay? All right? That big, this big particular thing will become a very small, this one here, example 6, will become very small, okay? All right. Okay, let's now move on, guys. Let's now move on. All right, I want to talk to you about another new topic. So I'm going to leave that one there as an exercise or homework for you guys. Let's talk about a new topic called universal gates. Universal gates. These are two types of gates. Now, what are universal gates? Universal gates are like basic building blocks with which you can build any other gates. Right? So, for example, if you are building a project, let's say some traffic light system or an alarm clock or some sensor system, right? And you need some gates. Let's say you need a couple of OR gates, couple of AND gates, couple of NOT gates, XOR gates, and so forth. And you go to the technician, and the technician says, sorry, I've run out of it. It's not in stock, which is a very common thing in engineering. A very common problem in engineering is not the design, but supply chain problem. Supply chain problem means you want some particular part, but it's not necessarily always available. So you as the designer have two options. Either you wait for the part to arrive, or you update your design with whatever you have, you build with whatever you have. Okay? And that's more what happens here in countries in the South Pacific, because if you wait for the part, it's going to come from America or come from China, and it will take maybe a month, and your project is delayed by a month. And in terms of project management, because most of you as engineers will end up as project managers, right? Losing 1 month's time is very, very big deal. Okay? All right, now, so you have these two gates, either the NAND gate, there are two possible gates, the NAND gate and the NOR gate, right? Okay, these two gates are gates with which you can build any other gate. So if you don't have a, let's say the technician or the store, the shop says, sorry, we're out of stock of AND gates, you can always build an AND gate using NAND gate. Or if you have only NOR gates, you can build it using NOR gate. So there comes another issue over here. The particular, what do you call, whenever we're building memory, even using NAND and NOR, like when you memory. For example, in any computer system, any calculator system, any arithmetic logic unit, you always have to have memory. Memory is the ability to store the bit. Over here, right now, up till this point in the lecture, in our EE222, we have not been able to store any memory. There's no capability for memory, all our circuits. You change the input, the output changes, right? Okay, even using memory, with memory we build within either NAND or NOR. Okay, so therefore these two types of gates are in high demand because they are universal gates. All right, let's start off with building. Build a NOT using, let's look at this one here. How do we build a NOT using NAND? All right, now I want you to consider the following. Okay. Now, which theorem is reflective of what we're doing over here? When you tie the two inputs together, what do you call that? Idempotency, right? Yeah, you must, all the theorems must be on your fingertips. Okay. If you have A going in and you have X, what can you tell me about the truth table? Yeah? You have flip 1 or 0. All right? So do you see that basically in the end, when you tie for an NAND gate, when you tie the two inputs together, the output is always the opposite. Yeah? 0 NAND 0 will give you 1. 1 NAND 1 will always give you 0. So when you tie the two inputs together, a NAND gate starts to behave like a NOT gate, an inverter. So that's how we built our NOT gate using a NAND gate. All right? Let's have a look at next one. We want to build NOT using NOR. What do you have? A, no, A. 0, no, 0. I want you to remember from your particular studies. If 0, no with a 0. 0 or 0 gives you 0, but 0, no 0, so you inflip that 0, you get a 1. Right? One, no, 1 will give you 0. So in the end, we can say that, hey, based on these results, when you have a configuration like that, even if you use a NOR gate, you end up with something like this. All right? Okay, very straightforward. Let's now do something more difficult. Okay, let's now build AND using NAND. All right, now, what is the NAND made up of? Okay, recall. Let's do a quick recall. A NAND, how did we build the NAND in the first place? How did we build the NAND in the first place? Well, basically, what we did was we built it by putting an AND gate in series with a NOT gate. That is A and B, then this becomes A and B bar. Now, obviously, what can we do? What have we just learned just 2 minutes ago? The NOT gate can be replaced with a NAND gate. You can build your NOT gate using a NAND gate. All right? But, hey, hang on. The question says build AND using only NAND. Maybe the word only is missing. Right? Build AND using only NAND. Okay. Now, we have if you consider this and we want to convert that into an AND gate, all we've got to do is right? That's our NAND output. So that's A, B, that's A and B, that's A and B bar. We want to revert back to this. So what do we have to do? Just place another inverter, then becomes A and B double bar, which is equals to A and B. Yeah, makes sense now? This should all make sense to you guys. This is not rocket science. So in the end, we can just say this over here, this part here was a NAND. So we can say that we have a NAND followed by a NOT gate, which is built using a NAND. That's A, B. This is A and B bar, and this becomes A and B. All right? Okay. So if we say over here, this point Y, this is X, we can say that Y is equals to A and B bar, X is equals to A and B double bar, which is equals to, so Y you can say is equals to X bar, therefore X is equals to A and B. All right? And for your homework, I want you to draw the truth table. All right? So every time, I'm not going to do everything, I'm just going to explain the hard parts. All the remaining parts you've got to do on your own. Okay. Let's now do the same thing. This time I want us to build, or using NAND. Right? Okay. Now let's recall. Recall no. Let's recall from our memory what is no. That becomes A or B node, right? And this is the same as saying an OR gate connected in series with a NOT gate. So same principles apply. Therefore, in order to build an OR gate from a NOR gate, all you've got to do is flip it over again. So therefore, right, you have I think we just say NAND or no. So we have this here, and then you put in another no, and same principles apply. So you've built an OR gate using NOR gates. All right? Okay? Right. This was using no. Now let's consider, I'm going to leave some space for using NAND. And we're going to come back to it. So using no, using NAND. All right. Let's now come back to it. Right? Or using NAND. Right. Now you have X is equals to A or B. Right? Now another way to look at A or B is you put a double bar. Right? Okay? You recall the double bar? Double bar is the same thing, involution. Remember the word involution? Okay? All right, now using De Morgan's theorem, in De Morgan's theorem what do? We break the lower bar. You break the lower bar and you change the sign. You break the lower bar and you change the sign. So what we are saying over here is, that's a NAND gate Yeah, we're using De Morgan's. Guys, I'm mentioning a lot of things over here. You might want to write it down. All right? And some of the things, I'm going fast, you guys can figure out. Like if you've written this down, you know how to draw that. Right? You should know how to draw that. Okay, let's now further expand that. How do we get an A bar? So x is equal to this. So actually x over here in this case is A bar NAND with B bar, which is the same as, if you want to further expand that, how do we get that? A bar NAND with B bar whole thing barred. You break the bar on the top and you change the sign. If you break the bar, that becomes double bar. So it's A or B. All right. Now, let's using, what have we built so far, guys? We've built an OR gate. We've built an OR gate using NAND. We've built an OR gate using NOR. All right, fine. OR using NAND and OR using NOR. Okay. All right. Let's now build AND. Have we built an AND over here? Yeah, we've built an AND using NAND. So which one is missing from our basic gates? Remember, there are 3 basic gates which we always build. The 3 basic gates are AND gate, OR gate, and NOT gate. These are the fundamental. We use them everywhere, right? The 2 universal gates are NAND and NOR. You can build any gate using NAND and NOR. XOR and XNOR are secondary gates. You have to build them using a lot of gates, a few gates. Okay? All right. Now, let's now build AND using NOR. All right, let's do some Boolean algebra here. Consider Z is equals to A or B. A and B. That is our target. Right? Now, from a mathematical point of view, you have, from Boolean algebra point of view, if you put a double bar, due to involution, it doesn't change anything. Right? Now using De Morgan's theorem, we break the lower bar and you change the sign. Okay, so we can draw it as this. There we go, which is the same as saying A bar, B bar into a NOR gate will give you Z. And these two, well, how do we get A bar and B bar? Well, in order to build it completely using NOR, right, we do it like this. We can replace the bubbles by building a NOT gate, using NOR, like what we've done early on. This here becomes A bar, that becomes B bar. Z over here becomes A bar or B bar whole thing barred. And according to the Boolean algebra which we've learnt on early on, that's equal to A and B. Right. Now, I'll give you some homework. We're not going to finish it all, but I've given you the fundamentals. Right? Some gates are still left. Right? I want you to, as homework, and hey guys, this is not primary school where I'm going to check your homework. This is for your own studies, because the exam, even though right now we are in week 4 or 5, we've lost some lectures due to the public holiday and so forth. You may find everything easy, but soon it's going to ramp up as we go along. As you notice, like today's lecture, what I was discussing in the first 5 minutes or first 10 minutes was again used later on just 2 minutes ago. All right, so we're recycling a lot of things. And if you're not comfortable with the Boolean algebra and so forth, you will start to fall behind. Now, so homework, I would like you to look into building XO using NAND. Right? Using what? How will we build this? Can somebody tell me? We just did this early on in today's lecture. A XO B is same as saying A bar and B, or B and A bar, yeah, or something along those lines. Yeah, we just did this in this lecture. So all you've got to do is you've got to expand that. All you've got to do is you've got to expand that. Now, I want to show you. Consider this particular circuit. Right? Use the formula given in at the start of lecture 1, week 5, lecture 1. All right? Okay. Now this is another one. Alternative circuit for XO using NAND. I want you to take into account this one here. This is an alternative circuit. This will be, when you draw that formula, if you remember the formula which I've just instructed you, this will be different from this. But they are both XO. They are both XO gates. Okay? All right, so homework continued. I want you to, okay, number one was to build the XOR gate using NAND, use the formula which was given. Which formula was that, guys? This one here. If you are not looking at your work, then you will be falling really behind. This one here. That formula. Okay? But we've got to convert this circuit into NAND. Convert into NAND only as part of homework 1. As part of homework 1. All right? Convert into NAND only as part of homework 1. The one which we just did at the beginning of the lecture. All right, now, some of the other things. And the reason why I give you homework, guys, is so that it can, you can do some problems in your free time apart from the tutorial problems, and this will be all coming in your short test. We are not too far away from your short test, somewhere around week 6 or so. Okay. So number 2, we've got to do a truth table for the alternative circuit of XO. Number 3, I want you to build XO using no, right? Use the formula. Use the formula or expression. Then I want you to do X no using NAND. That's not too hard. You just build XO and you put in a NAND gate. Then I want you to do X no using no. All right? And number 6, algebraic proof of the alternative circuit, right, for XO, what I've just shown you. All right, guys. Okay. Now, I'm going to just have a chat with you guys. I'm going to talk to you guys. And I want you to write down these 10 reasons for reducing circuits. What are the 10 reasons? Why are we applying this Boolean algebra and all that? So I'm just going to talk to you guys and you guys can jot it down, all right? It's not too hard. Number 1, it's obvious. When you reduce the circuit, what reduces, man? The cost, right? Fewer number of chips, fewer number of gates, the cost reduces. And we've done that in the tutorial as well. Number 2, what else reduces? Complexity. Yeah, complexity, because you've made the circuit simpler. You've made the circuit simpler, so you can. It's something which is only got 2 gates is easier to troubleshoot. So complexity is simpler, therefore troubleshooting becomes easier. Number 3 would be the space. You see, if you have 10 gates, let's consider the one which we were doing in example 1 and 2. If you have 10 gates, you reduce it to 2 gates, you also reduce the size of the circuit board. You don't need so many chips anymore. You need only 1 or 2 chips, right? Number 4, energy consumption. As you reduce the circuit, the number of chips, as you reduce the Boolean algebra, you reduce the circuit size, you reduce the number of chips, therefore you also reduce the energy consumption, because you only need to power 2 gates in order to achieve the same output. What number are we on? 6? 5? What number? 5 is done? Now 5. Okay, number 5. The other thing is, as you reduce the circuit, what do you reduce? In any electronic circuit, what does it emit when you touch it? Heat. Yeah. So when you reduce the size of the circuit, you reduce the heat. The heat, wastage of energy due to heat or heat exhaust, right? That's why you will see, and you can go and research it. Like Apple, they introduced a new chip. They introduced their new microcontroller, their new arithmetic or graphics chip, which doesn't need a fan. Doesn't need a fan. That's how much they were able to reduce. It's called the M1 chip. You can look it up in your free time. M1, right? M1. Number 7 was manufacturing time. Manufacturing time, what takes longer to manufacture, guys? Does it take longer to solder 10 chips or 2 chips? 10 chips. So when you reduce the number of chips, or when you reduce your circuitry using Boolean algebra, you reduce manufacturing time. Therefore, your company or your factory becomes more profitable. Instead of producing only 20 circuit boards in 1 hour, or 6 circuit boards in 1 hour, you can produce 20, because it's only 2 things you've got to put together, right? Okay? All right, now next one is manufacturing time, troubleshooting. Like when it goes for repair, right? A person will have like you as the engineer, will have a much harder time in repairing something which is very complex, right? For repairability, troubleshooting and repairability is easier for something which is simpler, right? Okay, the next number, which number are we on? I've lost track. 8 would be the weight. Remember in the old days when you used to carry a mobile phone, they used to be this big and that heavy, you know, like a brick. They used to call it a brick. Now, yeah, brick phone. Now it's very light. The more you reduce the circuit, the lighter you make it. That's why if you look at some of those laptops like Apple MacBook Air or whatever, very thin, very light. Okay? Right. Repairability, energy consumption. Yeah, and then obviously all this adds up to you save the environment. Okay? Okay. Profitability is the first point which I made. Right? Profitability comes from two things. Reducing the number of chips and also reducing the area, so circuit board, and also increasing productivity. Productivity means time to manufacture, manufacturing time. Right? So profitability comes from three areas. That's why you will have multiple profit increase. Not just the size of the chip, the number of chips, but number of the circuit board. You don't need to cut that much circuit board, right? Manufacturing time, soldering time, your factory workers will move, you know, produce more because it's a simpler board. Right? So this is the whole idea, and it's very common sense. I didn't need to give a lecture, but you should understand. If I ask you, how does reducing circuit time, reducing this particular circuit improve productivity? Then you can say, oh, well, productivity because the number of chips is reduced, therefore soldering time reduces, therefore our manufacturing facility will output more of these particular circuit boards. Okay, guys. All right. We'll probably stop over there, and we'll continue our lecture on tomorrow. Yes, we'll continue our lecture tomorrow. Okay, and we'll start up with a new topic. Thank you.